Hi guys, Mrs. McBride here. We are moving closer and closer to online learning. So some of the things we will be covering will become very important when we get to online learning. If you haven't done the review yet of 7.1 to 7.3, please go ahead and do that. That's on Canvas. I see that many of you haven't done that. And we are actually going to move on to trigonometric identities. Should we move on? I shouldn't say should. When we move on to online learning, these assignments are going to become required. So you might as well use your time wisely and start looking at some of these assignments. Okay, we're going to talk about trigonometric identities. I put here up on the screen some of the basic identities we've done before. Quotient identities, tangent equals sine over cosine, and cotangent, cosine over sine. These even odd identities I know have been confusing for some of you, but we did go over them in depth as to why they are. It all has to do with reflections across the x-axis. But I just want to make sure that you understand the basics of them. In an even function, the cosine of a negative angle is exactly equal to the cosine of the positive angle. So basically, on cosine and secant, if you see a negative angle, you can just kind of, well, I was trying to erase the negative. You can just kind of erase the negative. On the odd functions, which is everything else, sine, cosecant, tangent, cotangent, the negative, you can actually picture the negative coming out into the front. So the tangent of negative A is the opposite of the tangent of A. And then we have all our reciprocal identities, which you're super familiar with. And then we have the Pythagorean identities. Remember, if you want to go back and look at your notes, this is the important one. These two were derivations of this equation. And so I did show you in class how those were derived, so I would definitely go back and review those. So your directions on most of these, and you'll see it all the time, is establish the identity. Okay, so what does that mean? Well, it first means that they're giving you a true statement. Okay. They're giving you a statement that something is identical to something else. And what your goal is to prove the statement. Okay? And we use all the trigonometric identities that we've already discussed to prove that the statement is true. Okay, so let's look at our first example here. The first example we have is the sine of theta times the cotangent of theta plus the tangent of theta equals the secant of theta. What this is saying is this statement is true for any angle theta. Prove it. So what I usually tell people to do is not to work with both sides of the equation. You're trying to do a logical proof. Your work is your answer. So you cannot skip steps. We know what you're going to come out with. You're going to come out with reducing the left side of the equation to be secant theta. So it's not the end result that's your answer, it's the work all the way through. So you have to be logical, you have to show your work, you're giving a formal argument as to why something is true. So what I usually tell people to do is draw a line, right where the equal sign is, and work with the more complicated side. So in this case, and sometimes it's hard to tell which is the more complicated side, and I'll try to give you hints with that, but you're trying to make the left side reduce to be equal to secant theta. So you look at the left side of the equation, and the first thing you ask yourself is, can I do anything algebraically? And that means distribute, factor, give things common denominators. I'm pretty sure you guys would all see that you could distribute this sine theta. So I'm going to go ahead and do that. So what I would end up with is the sine of theta times the cotangent of theta plus the sine of theta times the tangent of theta. Okay, now that you've done that, you may say, well, there's really nothing else algebraically I can do. And if that's the case, and you can't figure out anything else to do, you can always replace everything in terms of sine and cosine. So what I can do is I can replace cotangent with cosine over sine, and I can replace tangent with sine over cosine. So let's go ahead and do that. I still have this sine of theta. I'm going to replace cotangent with cosine theta over sine theta. I'm going to leave this sine theta and replace tangent with sine theta over cosine theta. Okay, could I have done that from the beginning? Could I have replaced tangent and cotangent from the beginning? Absolutely. Okay, so now, as you can see, I can cancel this sine with that sine, and this side just leaves me with cosine theta. Here, the signs don't cancel, so you're multiplying fractions. If you have to think about this as being over 1, what you would have is sine squared theta over cosine theta. Oops, no. So now you're still not quite to your goal of making this equal to secant theta. So now again, you got to go back to thinking algebra. Maybe these are two things I'm trying to add, so they need to have common denominators. So in order to add these things, I need to put this guy over 1, and I need to give him a common denominator with this guy over here. So I'm going to multiply top and bottom. And remember, if you multiply a fraction, you have to multiply top and bottom by the same thing. This would become cosine squared theta over cosine theta plus sine squared theta over cosine theta. Okay, now that my fractions have common denominators, I'm going to go ahead and combine the numerators and put them over the common denominator. So what I would have is cosine squared theta plus sine squared theta all over cosine theta. Okay, and remember your Pythagorean identity. What is sine squared plus cosine squared always equal? Yep, it's 1. So you have 1 over cosine theta, which we know is secant theta, which if I scroll all the way back up to the top, oops, that's not how I scroll, you can see that that's exactly what I was trying to prove. So what I usually then do is just sort of carry this side all the way down. And then my last step would be secant theta equals secant theta. So the end of your identity should always look like this. Something equals itself. Okay, let's try them. I'm just going to give you 3 examples that sort of show little tricks that I'm trying to get you to see. And then the more you do these, the more you'll see patterns, and you'll be able to sort of repeat these tricks in other identities. So the cosecant theta minus the cotangent theta equals the sine theta over 1 plus cosine theta. Okay, so this is one of those ones where you may say, hey, I don't really understand which is the more complicated side. Well, if you notice that the left side is 2 terms and the right side is 1 term, it's always much easier to take 2 terms and bring them together than to take 1 term and split it up. So I think I'm going to again work with the left side. The only thing I can see to do, I can't apply anything algebraic, is to change everything to sine and cosine. So I'm going to replace cosecant with 1 over sine. I'm going to replace cotangent with cosine over sine. Could I have replaced cotangent with 1 over tangent? Well, yeah, cotangent is 1 over tangent. But I chose cosine over sine because now these things have common denominators. So once they have common denominators, I combine the numerators and I put it over the common denominator. Okay, now here's where the little trick comes into play. This does not look at all like the right side of the equation that I want it to look like. So I kind of always keep my end goal in mind. If you notice, this side of the equation has a 1 plus cosine in the denominator, and this side does not. So can I create the left side to have 1 plus cosine in the denominator? Sure, I can multiply top and bottom by 1 plus cosine. Now, what I always tell people to do is multiply your numerators, but don't multiply your denominators. Chances are something in your denominator is going to cancel out. If you notice something about the numerators, they're conjugates. It's basically difference of squares factored out. So when I FOIL those back together, that's going to become 1 minus cosine squared theta. And again, the denominators, I'm not going to multiply together. So I'm just going to leave it 1 plus cosine theta over sine theta. Okay, according to your Pythagorean identity, we can always replace 1 minus cosine squared with sine squared. So I have sine squared theta over 1 plus cosine theta times sine theta. Now this sine theta cancels with one of those. And so I'm left with sine theta over 1 plus cosine theta, which, if you go back to the beginning, was exactly what we were trying to prove. Okay, so what was the trick here I wanted you to see? I wanted you to see right here, if I wanted to create a 1 plus cosine in my denominator, I just did it by multiplying top and bottom of the fraction by 1 plus cosine theta. Okay, let's try one more. Try not to make the video too long. Example 3. The cotangent squared theta equals cosecant theta minus sine theta over sine theta. Okay, so in this case, I think I'm going to work with the right side. The only thing I can see to do is replace cosecant theta with 1 over sine theta. So I have 1 over sine theta minus sine theta. Oops. Do that. All over the sine of theta. Now, I can't tell you how many people want to cancel this sign with that sign. And you can't do it because this sign is attached with a subtraction. You can only cancel across multiplication. Okay, so now the trick I want to show you here, this is something called a complex fraction. You have fractions within your fraction. So the best way to deal with complex fractions is to look at These are sort of all over 1. If you want to put these over 1, you can. To look at all your denominators. So my denominators are sine theta, 1, and 1. So you say, okay, well, what's the least common denominator there? And the answer is sine theta. So what you do is you multiply the top of the big fraction by sine theta and the bottom by sine theta. And then you distribute it. So I distribute the sign here, I distribute the sign here. So sine times 1 over sine is 1. This becomes sine squared. And your denominator becomes sine squared theta. Okay, we're just about done. According to your Pythagorean identity, you can always replace sine squared, 1 minus sine squared with cosine squared. So cosine squared theta over sine squared theta. Oops, it's an ugly squared. Now we know cosine over sine to be cotangent, so cosine squared over sine squared is cotangent squared theta, which is what we were trying to prove. Okay, so the trick here that I was trying to get you to see is how to deal with complex fractions. When you have complex fractions, you always look at all the denominators and then you multiply top and bottom by what the common denominator would be. Okay, so there's an assignment attached with this. Go ahead and try it. We'll try to meet again at the end of the week. I don't know if they're putting together office hours for us. There's talk of that, but I will be in touch with you as to when I'll be online and we can talk about questions regarding this. Okay, guys, thanks a lot.